Good morning. This is the first segment of section 2.1 and is the first segment of chapter 2. So the first thing I just want to kind of say about chapter 2 is that we're going to split this up into, typically in a semester, I'll split this up into two sections. We kind of have the first few sections are more theoretical in nature and kind of describe some another way to look at trigonometric functions other than its definition, involving acute angles, and then we use that to extrapolate up to more complicated angles. You know, pretty much anything within the circle. But the first the first statement to make is that I'm going to do a couple proofs in this section because I think they're kind of relevant, and for those of you that may go on into any sort of other higher mathematics, doing proofs of some kind, at least some of the formal structure comes out of that. Now, I'm not going to do something as terribly formal as like in a calculus class or something beyond that, but I do want you to see how the logic leads to these sort of obvious, well, once you see them, obvious results. So this particular section, I usually spend a little more time on it than maybe the material that's in the textbook, but I think that it's valuable. So we may end up with 4 or possibly even 5 segments to complete all the ideas. So let me move over here to the document camera, and the first thing that I want to do is I want to prove to you the Pythagorean theorem. Now, this is something I'm sure, now when I'm in class, I usually ask students, I say, well, what's the Pythagorean theorem? And sometimes it takes a minute to elicit the response from the student. But as you recall, I mean, most theorems that you learn about in middle school or high school or wherever you learned them are kind of sing-songy mnemonics, right? And the mnemonic for the Pythagorean theorem is that a squared plus b squared equals c squared. Often people just lose perspective on what that actually means because they just get trapped in the idea of a squared plus b squared equals c squared, and forget that a, b, and c are very specific things. So let me start with, I mean, we've already kind of used the Pythagorean theorem, especially it's embedded in the distance function, but maybe this is a good place to talk about it since we are going to be talking pretty specifically about triangles now. So here's what the Pythagorean theorem says. So this is the Pythagorean theorem. So what it says is, if you have a right triangle, and remember, a right triangle is one that has one right angle. So if you have one right triangle, the two legs of the triangle, so the legs are the ones that are not opposite the right angle. And I'll say A and B. Now remember, when we're talking about the length of those legs, and the hypotenuse, I believe that's in, oh gosh, maybe it's this way. I'm not the best speller of Greek words. Hypotenuse of the triangle C are related in the following way. And this is where the a squared plus b squared equals c squared. So if you have any two of these, you can find the third one. Now, the hypothesis has to be satisfied. You must have a right triangle, and the names and the links associated with the legs must be labeled A and B, and the hypotenuse must be labeled C. If you change the labeling, then you change the formula, but the formula still holds, and it is arbitrary. Any right triangle has this property. So let's try to prove it. Now, to do any kind of, and we haven't really set up any axiomatic things or anything like that involving geometry, but I think it's fairly safe to say that it would not be too hard for me to convince you that the area of a rectangle is the product of the length times the width. Okay, and that's I mean, proving area properties is actually fairly complicated in geometry, but if you're willing to give me that little bit of leeway, I can prove the Pythagorean theorem. So let's suppose that, assume that the area of a rectangle with with height A and base B is given by area. Let's say, kind of label what A is. So assume that the area of a triangle A with height little a and base little b is given by area equals A times B. Okay, so we've assumed that there's a formula that we can calculate area from, assuming that we know the sides of the rectangle. Now, the first thing I'm going to do is I'm going to do a little bit of geometric proof, which means that I start by drawing things. So arbitrarily, here's my rectangle. And remember, this is sort of another thing we should note is that a square is a very special kind of rectangle. But rectangles have the property, and this is something that you do in plane geometry, where every corner is a right angle, and there is a unique height. So A doesn't matter which side you're looking at, B and B. Now, what I'm going to do is I'm going to first, and maybe I won't write it all down very formally, but let me just start with this. I'm going to connect the two opposite corners. It doesn't really matter which one I pick, but let me just pick this one. Okay, and I will label this length C. Now at this point, you have two triangles, and we could label them with letters and everything else, but it should be pretty obvious that these two triangles are congruent, and you can use several different arguments for that. You could use a side angle side, you could use a side side side, but the reality is that both of these two triangles are congruent, and if two triangles are congruent, then their areas are equal as well. And that's one of the things we stated early on. Now, that's not something that's usually stated about congruent triangles, but is actually true. So if I have two triangles whose area adds up to A times B, and both of those triangles have the same area, so I could say something like this. So 2 times the area of the triangle is equal to the area of the rectangle. And I'm using some subscripts to represent which area I'm talking about. So that means that the area of these individual right triangles is equal to 1/2 the area of the rectangle, which we have as a formula A times B, so it's 1/2 A times B. So the area of a right triangle is given by 1/2 the product, 1/2 times the product of the legs. So we haven't said anything about regular triangles. I mean, regular triangles, we could have started with the idea that we could have used that old adage that the area of a triangle is 1/2 base times height, right? And it doesn't really necessarily have to be a right triangle, but and that can be proven from this result, because what you basically do is then you create a triangle that's actually broken into two right triangles, and you see that the sum actually is the base times the height. But we don't need it, so let's not get ahead of ourselves. We're really only starting with the assumption that area is computed in a very specific way. So now what do we do with that? So what I'm going to do, and whether people realize it or not, there's a buried assumption about how areas work, that if you have two shapes that have an area and you stick them together, that the area of the sort of composite shape is the sum of the two areas. That's kind of not necessarily required out of a mathematical structure, but it does make a lot of sense. So it's not a huge stretch. And again, this isn't really a geometric proofs class, but so I'm going to assume that you're allowing me certain liberties. Okay, so now that we have sort of these results, we know that the area of a rectangle is the base times the height. We know that the area of a right triangle is 1/2 the base, the product of the two legs. So let me start by drawing a very specific square. Now remember, a square is a special case of a rectangle where it has right angles at every corner, but that the sides are all the same length. So we could start by saying, well, that's a right triangle, or that's a right angle, and that's a right angle, and that's a right angle. Now what I'm going to do is I'm going to break up these sides into special same lengths. And if I was a great artist, which I'm not, you would see that that is also a square. But let me do A, put some labels on things, B, A, B, A, B, A, B. Now, why is that assured? Well, that's the controlling factor, is that I break up the total length, A plus B, at some specific points. Since they're the same on all sides, this is an okay procedure. Now, the question that one might ask is, are these all the same triangle? Well, are they all the same? Are all these triangles congruent? And yes, they are. And you can make that statement with just a side angle side, right? You have side, right angle, side, side, right. So they're all congruent to each other, and therefore their areas are equal. Now the question might be, what is the shape of this thing in here? Well, we know that it has the same lengths because these are all congruent triangles. Now the question is this actually a square? And the only requirement that's left is for it to be right angles at these specific points. And of course, yes, the answer is it is, because here's one way to think about it. The sum of this angle and this angle has to be 90 degrees, right? Because the sum of the interior angles of the triangle is 180, 90 of it's taken away by a right angle. So you have sort of this angle, this sort of more shallow angle, and the little bit more obtuse angle, but they're still acute. But notice this angle and this angle are the same angle. So this angle and this angle add up to 90 degrees. But if you look at the whole thing, that's a straight angle. So you have 180 degrees minus two things added together that equal 90. What you're left with is a 90-degree angle. And we could repeat that argument at every one of these corners, but the net result is that we have a square within a square. Okay, so now let's do two things. Let's first do a computation that gives us the area of the larger square, okay? So the area is, again, is for a rectangle, and a square is a special case of a rectangle, is the product of the length, or the base times the height, which in this case is actually the same number. So it's A plus B squared. And if we factor this out, we FOIL out that result, this will be A squared plus 2A times B plus B squared. Okay, so now that we have that, let's construct the area by adding up all these parts. So you have the square that's in the middle with lengths C, and then 4 separate triangles with legs A and B. And remember, so this is the same area, right? It's the same big square. Notice that we're going to have 4 triangles, which have an area of 1/2 A times B, and then we have this interior square whose area is just c squared. Now, since these two areas, these two sort of formulas represent the exact same location or area, these two formulas are actually equal to each other. And I'll go ahead and simplify this one. I've got 2a times b plus c squared. So, and this is a common trick that we do in a lot of these sort of algebraic geometry things, is we say, well, here's a formula for it this way, and here's a formula for it this other way, and look at this neat result. So by setting them equal to each other. So since a equals a, the right-hand sides of these equations are equal to each other. So I have a squared plus 2a times b plus b squared is equal to 2a times b plus c squared. And notice I have a 2a times b on both sides of this equation, and so I can cancel them. And what I'm left with is that a squared plus b squared equals c squared, which was what we wanted to show in the first place, right? So this is a very sort of quick proof of the Pythagorean theorem. And now that we sort of have it, I think that I can use it with impunity. But of course, there are many applications to the Pythagorean theorem, and we've already seen some of them. But basically, what we're working towards is wanting to be able to solve triangles. And solving triangles means finding all angles and all sides. And we may have bits of information where maybe we know two sides and we need to find a third one, which we have done. And then we use the trigonometric functions to find angles or vice versa. So anyways, I think that's it's kind of a short proof, but it's a place to stop. I will come back in the next segment and we'll start applying this to some interpretations of trigonometry. So I know this video might be a little bit short, but I assure you some of the other ones will be a little bit longer. Okay, I will see you.